Good afternoon, EFD 620 students. I hope you're doing well. Thank you for your involvement in the class, your patience, your emails, and all the communication that you've been able to send. I appreciate that very much. We're here to talk about statistics. Probably there will be two short videos regarding this subject, and the reason that we're having this particular module and unit of study for our course is because I'm responding to two things that were indicated in the survey that I sent at the beginning of the term. One was some were suggesting that we need a review of statistics, simple statistics, and I will offer that. The other is many of you, quite a number of you, indicated that you might pursue another degree, a doctoral degree, a terminal degree, and if so, this statistics overview will be of help to you. The PowerPoint that I'm going to use now will also be available to you on Blackboard, but I'm going to talk our way through it a certain point, and then we will pause and then begin another session. So thank you very much for your attention and attentiveness to this module. This is going to be a concept summary of what I would call major elementary concepts. Understanding terminologies and concepts about statistics is really what a person needs to have in this day and time. You do not need to know necessarily how to compute basic statistical tests. You have various computer programs that can do that for you. But we do need to know some basic terminologies. We know what the mean is. The mean is the arithmetic average. Add up all the scores, divide by the number of scores, you get the mean. You understand that. The median of a group of scores or numbers is the midpoint of that group of numbers. Half of the scores are below that, half are above that. The median may be at one of the scores, or it may be between two of the scores. The mode is the most frequently occurring number, or the most frequently occurring score. The mean, the arithmetic average, is most affected by skewness. To give you an example about that, this is one of the reasons why the United States government in census data reports income and socioeconomic status by the median family income, not the mean family income. For example, if you were living in the town or the county with Bill Gates or Ted Turner, then the average income is going to be skewed greatly by that particular outlier. If, on the other hand, in that same county you had an extremely wealthy person, then you would still have the same median. That is, an equal number of households below the median, an equal number of households above the median. So Census Bureau socioeconomic numbers are reported by median family income as opposed by the mean family income. The normal curve is, or the bell curve, bell-shaped curve, is something that you must be able to understand. It's going to come up on your praxis. It's going to come up on any kind of advanced degree test, and certainly you have to be aware of it, and it's used in many different statistical analyses of any kind of assessment whatsoever. The normal curve simply means that in any random population group, randomly selected, a normal population group, regardless of what the particular parameter is that you're discussing, the numbers will fall out in this particular manner. You will have 34% of that population group that lie between the average, the median, and one standard deviation below the median. You'll have 34% between the median and one standard deviation above the median. You'll have 13.5 or 14% between 1 and 2 standard deviations above and below. For example, if we're talking about intelligence scores, IQ scores, we know that the average IQ score is 100. The standard deviation in the Stanford Binet and other tests is generally 15. So you have 34% of a normal population group that are going to have an IQ between 100 and 115. You're going to have 34% of that population that have an IQ between 100 and 85, one standard deviation below the mean. Then you're going to have another 14%, add that to the 34, you're going to have 48% of the population, this area under the curve right here, you're going to have 48% of the population that have an IQ between 0 and 130. You're going to have another 48% of the population that has an IQ between 100 and 70. And you know that 70 has generally been the cutoff score for special education services in terms of mental deficiency or mental handicap or intellectual disability. And then you have in each of the tails, T-A-I-L-S, of the curve, you have about 2% of the population down low and 2% of the population up high. For example, you will have 2% of the population that will have an IQ score above 130, and you'll have about 2 out of 100 people who have an IQ score below 70. So it doesn't matter if you're talking about height and weight distribution or things like that. The normal curve, if you get enough people in a sample and they're randomly sampled, regardless of the metric you're looking at, the population is going to end up something similar to this particular normal curve. Here are a couple of videos links that I wanted to show you, and you can look at these, and they're real short, but I hope you will take time to watch those particular 2 YouTube videos about the normal curve. I mentioned skewness. This is when the population is weighted or slanted in a positive or a negative direction. We mentioned that the mean is what is affected most by skewness. In this particular case, on the right hand side of your screen, when you have a mean, an average that is lower, that means there's probably more people in the upper part of the distribution. So you can see how the curve changes when you have more people who move to one direction or another under the distribution itself. Another characteristic of distributions is called kurtosis. This has to do with the flattening of the normal curve itself. It is a normal distribution, and then if there are an awful lot of people who are near the mean, we're talking about this high curve here, if there are many people who are near the mean and most of the subjects are clustered closer to the mean, then you're going to have a positive kurtosis. On the other hand, if you have a wide distribution, and the scores or the numbers are distributed widely, not around the mean but away from the mean, then you're going to have a negative kurtosis, a shorter, flatter curve, which still has some characteristics of the normal curve, but it's flattened out, illustrating that you have a wider distribution. Let's talk a little bit briefly about a couple of tests, and then we'll take a break from this particular session. A t-test is one of the most robust and often used tests that is used statistically. A t-test is used to test the difference between 2 means. It is a very robust or powerful test as far as statistics go. That is, you can depend upon the results, and it is very applicable. For example, if you wanted to test the difference between the average math score of an 8th grade class in one of your schools in your county and measure that against the average math scores on perhaps the NAEP or Global Scholars of another classroom in another school in your county, You could test the difference between those two means using a t-test. The t-test would show you if there is a statistically significant difference between those two classroom averages. When we say statistically significant, what we're really saying is that the difference is a genuine difference and not simply due to chance. Okay? Here is another very good summary of t-test in a real-world example, and I encourage you to look at that. T-test, very robust. The question is, can you test between 3 classrooms or 4 classrooms or 4 schools using a t-test? And the answer is no. The test loses its power exponentially as you repeat the test again and again between different groups. And so we have other ways of doing that. So a t-test is simply used to test the difference between two averages, two means. What do we do when we have multiple means? Like we have multiple classrooms. You have 8 schools in your district perhaps, and you want to test the difference between or compare the 8th grade math scores between all of those classes. So we have 8 means, 8 average scores of all those classes. We use an analysis of variance. We cannot just do multiple t-tests. Every time you repeat a t-test, it's less powerful and increases the chance of a type 1 error. A type 1 error means that you will reject the null hypothesis, which says there is no difference between these two, and you will reject it when there really is no difference, and by rejecting it you're saying there is a difference. This is another example of ANOVA. I plead with you to look at this particular video. So we've looked at how you can compare averages across the board. Analysis of variance for multiple averages or means or groups. T-test if you have only 2 that you want to score. Let's talk about those type 1 and type 2 errors right quick. A type 1 error, or error of the first kind, is the incorrect rejection of a true null hypothesis. Now, the null hypothesis in statistics is stated negatively, empty. Null means empty. There is no significant difference between the means of group A and B. That would be the null hypothesis. And so if you reject that hypothesis that is true, that is, there's no significant difference, and you reject that, what you're really saying, what the mistake you're making is that there is no difference between the two, and you're saying that there is a difference between the two when you reject that null hypothesis incorrectly. So you're coming to a statistical conclusion of research that is an incorrect conclusion and could be devastating to a school or a system. If you're saying there is there is a difference, you reject that true null hypothesis, there's really a difference, but there's really not a difference, then you're going to be spending money and spending time and doing interventions and things like that when there's no statistical reason to do so. A type 2 error is the failure to reject a false null hypothesis. Again, the null hypothesis is there's no significant difference. If we find it to be true, that is false, then the null hypothesis is now saying there is a significant difference. Okay? If we don't reject that false null hypothesis, then we're agreeing that there is no significant difference. But our statistics say there is a difference. And again, we're ignoring that there may be a difference between the two classes. So wrap your head around that, and I don't think that will be a problem.